Okay, so I am going to quickly talk through the solution of this exam. I think it is from 2014. You all should have the solutions. The first thing is you've got to understand that we have in statics, we had internal forces. We had internal normal, shear, moment. Normal just means perpendicular to the area. Okay? So when I look at normal stress, it is like a rubber band, and I'm pulling and I am perpendicular to that cross-sectional area. It is always sigma. Sigma is always normal. When I say sigma, normal stress is P over A. I can also say, okay, what equations go with that? Because they're kind of spread out, and I can see a sigma down here. So we have P over A, and then we also have the relationship for my force in area, the material property, and strain. Okay, well, what is strain? Well, strain is change in length over length. It has to do with how much stretch we have. If I have a rubber band and I pull on a rubber band, it's going to have a lot different stretch than if I try to put the same force on this pin. So I can have the same force in area, but because my materials are different, I'll have a different strain. Strain is always delta. Delta just means change. If I have a change in temperature, a change in weight, a change in force, a change in length, delta just means final minus initial. Length final minus length initial. It can also be diameter final minus initial. So we could have diameter final minus diameter initial over diameter. We could have base final minus base initial over base initial. Strain is just, it doesn't matter what you're looking at, it's just change in length, okay? So I can see that these are related, and they end up, when I put them together, they make my delta equation, okay? If stress equals P over A, and that equals E times strain, which is E times change in length over length, that's how I come up with this equation that I can rewrite. It is just putting together my normal stress equations. This was from chapter 1. This was from chapter 2. This was from chapter 3. This is from chapter 4. I just put it all together. Okay? When I look at shear, okay, shear means, go back to statics, parallel. Okay? Shear means parallel to my plane. So it is, if I have a bolt or anything, it is that force that is now parallel to my plane. That's what shear means. It's parallel. Shear is tau. Okay? So if I have tau, it's okay. It's that V. It's that force that's parallel to my plane over A. When I see the tau, I can say, oh, well, here's a tau. It relates to this. Oh, here's my shear strain. So stress, it doesn't matter whether it's normal or shear, equals either E or G, okay, our material property, times strain. It doesn't matter whether I'm looking at the normal or shear. If I put a load on an area, I'm going to have some deformation, okay? And I know that we can relate shear stress and normal stress with this equation. And that's how we get Poisson's ratio, okay? So I'm trying to find a different color here. Let's go with pink, okay? So this relates normal, and this relates shear. And when I do that, I get Poisson's ratio, which is just how I go back and I can use strain. What is strain? Length final minus length initial over length initial. Length final minus length initial over length initial. So if I know the change in longitudinal, applying my load, I can get my lateral, my cross-sectional things. Okay? So you just have to have, that's all we're talking about. Material properties. I need to understand then E. E goes with my normal. It is, okay, the slope of my stress strain diagram. G. G goes with my shear. It's going with my shear stress, where's shear? Shear stress, shear strain, G. Okay? Normal stress, that means it's in tension compression. Okay? Shear stress, that means it's like a bolt. Okay? You need to know the difference between yielding and ultimate. Yielding is when we're still in that elastic region. So when I use this equation, I'm really looking at yield stress and yield strain are smaller. Okay, ultimate, so we'll talk about these in more detail. This goes with normal, this goes with shear, this goes with normal, this goes with shear. Okay, so you have to understand what you're pulling. These have to do with temperature. They're going to be on here because our next exam has temperature. We don't have temperature on this test. Don't be confused and be like, oh, do I need to use that? No, you don't. Okay, so stress strain curve. Okay, when I have two curves, this lower curve, okay, because this is the elastic region, our strains are so very small, we have this lower, okay, we have this lower amount of numbers on our axis. When I'm looking at the upper curve, find a different color. When I'm looking at the upper curve, okay, I have these upper values. This is my elastic region. I can't read these numbers if I wanted to. I couldn't read the strain. So we multiply our strain and we make much smaller numbers so that I can stretch out the elastic region. This is just this piece on a bigger curve. Okay, same thing. This is how I find E. E is slope of a line. E is slope. It is rise over run. It is yield stress over yield strain. Here's my yield stress, okay? And I can come across, and here's my strain. Okay, that's how I find it. Okay. So, when I'm looking at this problem, I'm given a load P, and I'm going to start with statics. And I can either draw a free body diagram of the top, and if I do it of the top, it's P over 2, because if this is 75, I have to be pulling back equal and opposite of 75, or we are no longer in statics, we are in dynamics. So overall, I am in equilibrium. I can look at this top piece, and if I'm pulling this way, the shear force under here is 37.5. So if I'm looking at the shear that's going across these bolts, so I have 1, 2, 3, 4, 5, 6. Shear is V over A. I'm going to have 37.5 divided by, okay, I have 6 bolts. That's my number of bolts. It's in single shear when I look at this, so that's single shear, and then pi over 4 d squared. I could look at this member with 75 kips, and if I do that, I have to recognize that our shear is being split up, okay, top and bottom. So I'm now looking at a double shear situation. I'm looking at two planes of those bolts. So I would have shear stress is V over A. So here I have the total 75, but because I'm in double shear, I have two areas, so that's double shear. I still have 6 bolts and pi over 4d squared. Now when I look at these two equations here, it's single shear, but I basically had a P over 2. Here I'm in double shear. Well, what is 75 over 2? Okay, 75 over 2 is 37.5. So you can't just say, oh, it's in double shear, but I'm going to choose this number. Or, oh, it's in single shear, I'm going to choose this number. You guys have got to start drawing free body diagrams. Okay? If I'm looking at this piece, then I am looking at the shear that's being transferred so that we can get all the way over here. So if I'm looking at this piece, I am in double shear. If I'm looking at this, then I'm looking at the shear. Remember, equal and opposite on the inside that's acting this way. I'm in single shear. Okay, so I'm going to use statics. And when I use statics, okay, these rigid plates determine the required diameter of the dowels. And it tells us that we're going to be using the allowable shear stress. So if we're working with dowels, if we see bolt, dowel, glue, glue. This is shear. We are looking at a force that's trying to shear that apart. Okay, the bolt is looking like this. The shear, do you see how it's parallel to the plane? Okay, bolt, dowel, glue, shear. If I'm using shear, I have to make sure that I'm using shear values. Shear values. Shear, shear. Okay, so if I'm looking at bolts, that's the way I have to do it. 3 rigid plates are connected with 6 dowels. Determine the required diameter to the closest 1/8 inch if the allowable shear stress is 1/2 of the yield shear. Okay, so it's a factor of safety. Yield shear. That tells me yield shear. Yield shear versus ultimate. Yield shear. So if I have a yield shear of 25 KSI, and I have a factor of safety of I want it to be 1/2, then my allowable shear is 12.5 KSI. And shear equals V over A. V equals, well, if I look on this side where it's in single shear, 37.5 divided by 6 bolts pi over 4 d squared. If I want to look at this side, it's going to be 75 over 6 times 2, because I'm in double shear, pi over 4d squared. So you just need to recognize bolt, dowel, glue, shear. I'm looking at tau. I could also look at the failure across this. So if I look here, if I wanted to look at this type of failure, this force is perpendicular to my area, so this would be normal, because I'm perpendicular, P over A. So I would have P over 2, and then it would be the thickness times the width. That would be the area that I would have failure if I wanted to also be looking at the plates. Okay? So it's key words. If I'm looking at a picture and my force is perpendicular to that plate, okay, normal. If I'm looking and I'm pulling and that force has to transfer through because I'm in equilibrium, we are now parallel to these internal cross sections, shear. Okay. So, stress strain curves. Again, elastic region is where I can stretch it and it goes back to the original shape. Stretch, original shape, stretch, original shape. So this is my yield stress. Up until this point, it stretches and goes back to the original shape. If this is my yield stress, this is my yield strain. This is where I can find E. E is my modulus of elasticity. E is the slope of the line. It is rise over run. It is stress over strain. It is 75 divided by 0.003. This is my ultimate. I cannot have any more stress than 100 KSI. That's the most stress. That is ultimate. That should be a U. Ultimate. Ultimate stress. This would be the stress, the strain that's associated with where I reach that ultimate stress. If this is my ultimate stress, here's my ultimate strain. This is my strain at fracture. That's where I fractured. Okay? So you just need to be able to understand this is stress, strain. And it goes right back to, here's your equation. Stress equals E times strain. Force over area, deformation. This is force over area. This is change in length over length. If I want to know the force, the load that causes yielding, well, a load is a force, and I'm causing yielding. So if I'm causing yielding, well, I'm yielding at 75, and if I want to know the force, well, it's just P over A. Go back and solve for P. It's just stress times area. Okay, the ultimate load is, well, what is my ultimate stress? It's 100 KSI. If I want to know the force, stress equals P over A. I have to just understand that this stress equation is literally P over A. Okay, so this is my normal. Here is my shear. I have a yield. That's where I get out of the elastic region. We now have that yielding. This is G, my shear modulus. It's just the slope of that line. This is the shear strain associated with yielding. And here's my shear strain associated with fracture. Okay? And I just need to be able to understand the definitions. Okay? I just have to understand definitions. If I say force, if I say load, okay, that is going to be units of pounds or kips. If I say stress, okay, stress is like it's a force over an area. PSI, KSI. So sometimes if you are having a hard time, like, what are they asking for? What are we asking for? Load, that's a force. Load, that's a force. If I said, what is the stress? Stress is KSI. Stress is PSI. Okay? If I wanted Poisson's ratio, I have that. You have to understand, well, what is Poisson's ratio? How can I find it? Poisson's ratio is this funky little V. If I can find E, which is the slope of my normal, and G, which is the slope of my shear, then I can calculate Poisson's ratio. Okay? And that relates my stress that makes something longer. It then relates that strain, that change in length of getting longer, to the change in length of the diameter getting smaller, or the diameter getting bigger if I'm in compression. It's just relating the geometry of my area. Okay, the cake problem. The first thing is, you all have got to get yourself a Post-it note, okay? If I want to find anything, deformation, stress, whatever it is, okay, I have to, just like statics when we had a beam and we loaded it, we had to draw our shear and moment diagram between where we had loads. So I'm going to come down, I'm going to cut it there, and I'm going to draw myself a free body diagram of 5,500 that's given, and I always assume tension. What are our internal forces? Normal, shear, moment. Okay, here's my normal. It's my force from B to C. I'm going to assume it's in tension. And then I'm going to sum forces in the y direction equals 0. I get minus 5,500 minus force BC equals 0. So force BC equals negative 5,500. That tells me it is in compression. I don't have to guess. I can look and tell you that's in compression. It's being squished. But the math will work out if you set up your statics correctly. Okay? If I'm going down, 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 boink, okay, cut. I have to include everything above. So now I have 5,500 and I have 6,000. So internal, I have force A to B. Sum my forces up and down, minus 5,500, minus 6,000, minus FAB equals 0. FAB equals 1150, 100, whatever that number is. It equals a negative. That means I assumed it in tension. It's really in compression. Does that make sense? Absolutely. It's in a compression. So now, if I want to know the stress from B to C, well, what is stress? It's the force in B to C over area of B to C. Negative 5,500 over 10 by 10. Stress in A to B equals negative 11,500 divided by 20 over 20. That's my stress. How do I find strain? Stress equals E times strain. If I calculated stress and I know it's steel, I go back. 29,000 KSI. I can then calculate strain. And what is strain? Strain is change in length over original length. It is length final minus length initial over length initial. Okay, you're just filling in. It's just, It's taking the same equation. I have to use the same equation, whether it's stress or strain or whatever, for every single section. And I have to include everything that's above my line. Or if it's going sideways, everything to the right. If I want to start with the support, I would have to come down here and find my reactions, because I would have to include the reactions as I went up. Otherwise, as I'm going up, if you don't have reactions, there's no force there, which we know isn't true. Okay? If I have yielding, so what if I find that my stress here, the stress here is greater than 36? My yield stress for steel is 36 KSI. So what if I find that my stress equals P over A, and I get a value for P, okay, I know that number, and I know my A, and I get a stress of 50 KSI for steel. Okay, if I get a stress of 50 KSI is greater than yield. I cannot use this equation. I can't use any of these equations because we are no longer in the elastic region. This region is just where I have rise over run. If I have yielding, then I go to my little stress strain curve, and this is for steel, and I can go to 50, and I can draw down, and I can look at my scale, 0.05 to 0.1, so that's about, I don't know, 0.085. That's my strain. I can just pull it right off the chart. Okay, so if I have 0.085, so if strain equals 0.085, that is length final minus length initial over length initial, and it was negative strain because I'm in compression. This is the value I'm going to use to find that final length. And it's going to be drastically different than if I used the elastic region. Okay? This last problem, this was on a quiz for a reason. If I pull here, then I'm going to have tension through my system. So I'm going to have a delta of my cable. And delta of my cable is the force in the cable, the length of the cable, the area of the cable, the E of the cable. I'm also going to pull on this block, and it's going to tend to skew. Okay, so if I know the force that's here, and the block is got a depth, okay, there's the top of it, then this shear force is acting on the top of my block, then the area that it's acting on is this top. So this is just like, go back and review that quiz that we had. Shear stress is V over A. Okay, this V is the force in the cable. This A is, in this case, 16. And that V is 10 kips. Okay, so if I can get the shear stress, and I know it's nylon, I know that shear stress is G shear strain. I can go get the G value for my nylon, and I can calculate the shear strain. That is the deformation. If I know that this is 8 inches tall, and I want to find delta, how much does it skew over? Well, with small strains, delta equals, gamma equals delta over that 8. So I can just take the value of gamma I got, multiply it by 8, and I now have delta. So I have delta of my block. And I have a spring, I can get delta of my spring. If I add all those up, that's going to be my delta B. Okay, it's just a piece, a piece, and a piece. And you've had all of these things on a quiz. So it really is just, you need to just understand to put the pieces together and kind of look at it as a system, but look at it also individually. That's a shear block. Oops, that's a shear block. We did that on a quiz. I think we had a spring on a quiz. Okay, I know we have this on a quiz. Find the internal force, find the stress, find the deformation. Internal force, find the stress, find the deformation. We've done all these things piece by piece on the quiz. Stress strain curves. What's the yield stress? What's the yield strain? What's the ultimate stress? What's the force that causes yielding? What's the change? all of this stuff, if you look at your quizzes, it is literally these exams taken apart into little pieces. So, anyways, y'all have a good night.